Good morning, dear students. Uh, Today we're having ninth practical lessons, and this lesson is about double integral in a rectangular coordinate system. Uh, Before we start uh, calculating integrals themselves, uh, first of all, we will have some practice in determining limits of integration in the integral. So which function is under integral, it doesn't matter as for now. So we just need to set correct limits. First of all, we need to plot this region. So the first region is a rectangle where x is from 2 to 5 and y from 0 to 3. So yeah, so such a region bounded by this straight line, so this rectangle. And we need to define limits of integration. So so actually this is the easiest case when we integrate by the rectangle, in the rectangle. So let's determine limits of integration. How to do it? So the integral will be the following. Uh, so firstly, let's assign. So in the outer integral, we will assign uh, limits of integration by x, and in the inner integral, we will assign uh, limits of integration by y. Actually, 1a is done, so that's what was required to do. Of course, yeah, so uh, when calculating double integrals, you should always plot the region to understand how to determine limits. Any questions about this exercise? Okay, no questions. So let's move next to 1b. We have another region bounded by the following curves. So we have a parabola, y square, not actually the parabola, but yeah, let's draw the parabola. Uh, so y square equals to x. Then y equals 0, x equals 0, and yeah, x equals 2. Not 0 by 2. So we have the following region. So and this one that we need to, yeah, so no, we know that y is uh, less or equals than 2x. So then x x and y are positive, and x is less than 2. So this region. So how to assign this limits of integration correctly? So we have two different ways. We can firstly so assign, yeah, so we can make y so is a outer variable. So bounds of integration by y are 0 and 2 dy. And for x, we integrate from y uh, square y square over 2. Oh no, y square over 2 is the uh, bottom limit, and the top limit is 2. And also we can uh, do it in another way. So we can assign we can change the order of integration. So firstly, the outer integrate will be by x, so x from 0 to 2. And what about y? Y has values from 0 to square root of 2x. And actually, these integrals will give the same result. Any questions about this exercise? Okay, no questions. So let's move next. Now we have to change order of integration in given integrals. So, uh, 2a, we have the following integral. So inner bounds or outer bounds from by y from 0 to 1, and inner integral from y to square root of y. And again, we don't calculate integral now. We just so all that we do, we just swap the order of integration. So it doesn't matter what is the function now under the integral. Again, uh, let's plot the region. So first of all, let's plot curves. So x equals y and x equals the square root of y. So actually, yeah, so we have such a region, so this figure, and we can see that y has value reaches value from 0 to 1 that matches this integral, and for x that from y to square root from y. So let's so how to describe actually this uh, region of integration in another way. So as we can see from the graph, x has values from 0 to 1. And what about y? Y reaches values from x. So here we don't have so not numbers but functions. So y is bounded by this function x square from the bottom and x from the top. So now let's rewrite this integral. So 0 from so x from 0 to 1, and for y from x squared to x. And that's it. Any questions about this exercise? Okay, I guess that everything is clear. Well, you will have to do more practice, and it will be more understandable. Now moving to exercise B. So the following integral, so limits from -1 to 1 by for x, and for y, y has values from 1 to x from 0 to square root of y minus x square. So actually this is the semicircle. So let's first of all adjust this. Yeah, let's plot the circle. So y equals 0 and y equals square root of 1 minus x square. So this is the region of integration. So x from -1 to 1, and y is bounded by these lines. So this semi-round. Now let's describe, so let's swap bounds of integration. So how can we describe this region? So for y, y reaches values from 0 from 0 to 1, as we can see from this graph. So 0, 1. And what about x? So from this quarter of circle to this quarter of circle. So from minus this square root of 1 minus y square to this square root with the sign plus. So now let's rewrite bounds of integration. So change the limits of integration. So y is integrated from, so integrate by y from 1 to, from 0 to 1, and by x from minus square root of 1 minus y square, and to square root of 1 minus y square. Any yeah, by the way, it was a mistake here, so now everything is correct. Any questions about this exercise? Okay, no questions. Now we have a more complicated case, but actually nothing impossible for us. So so we have sum of integrals, and we have to change bounds of, so limits of integration. And plus, so the second integral is from 1 to 3 by x, and for what about y? So from 0 to 3 minus x over 2. So let's plot this region, and then we will understand what to do. So let's plot all this bound, all these curves. So y equals 0, then y equals x square, and y equals so y equals the following straight line. And what about x? So what do we have? So we have the following region. So for the first integral, we have such bounds. So x from 0 to 1, and y is from 0 to x squared. And what about the second integral? So we have the following region. So so x from 1 to 3. So correct. And y from 0 to this straight line, 3 minus x over 2. And now let's describe this region in another way. So, let's stop annotation. So, let's describe y first of all. Y reaches values from 0 to 1. So now it will be out a variable. And what about x? So let's let's transform x. So it will be equal square root of x. So square root of x, and we need to find x from this equation. So no, stop. Yeah, square root of y. Sorry, square root of y, and for this straight line, so we need to solve this equation with respect to x. So 3 minus x will be equal to y, and x will be equal 3 minus 2y. So now we can change limits of integration. And now, yeah, so we can see that this is kind of irregular region of integration, but if we change bounds, if we change limits of integration, we will receive one integral instead of a sum of integrals. So that is actually easier to and more convenient to calculate instead of two integrals. I guess you agree with it. So so we integrate by y from 0 to 1, and what about x? We integrate from square root of y to 3 minus 2y. So any questions about this exercise? Okay, I guess that no questions. Moving next. But first of all, cleaning all drawings. And now we will calculate double integrals. So let's calculate. So actually, we will do the stuff analogical to function of to differentiation of function of multiple variables. So we have the following integral. So function is x squared plus x cubed plus y cube, and the region is the following. So we have the triangle bounded by the following line, straight lines. So let's plot them. So y equals x over 2, y equals x. And x equals 4. So we have the following region. So we have such a triangle, in which we will integrate. So let's assign bounds of integration. So I recommend to integrate. I recommend to set the following bounds. So we will integrate by x. So x will be an outer variable. So, and it will reach values from 0 to 4. And y will be inner variable. and it will have values from x over 2 to x. So now let's rewrite this integral. So now let's integrate let's calculate like a usual integral. So what will we have? So when we integrate by y, we think that so the x will be taken as a constant. So analogically to partial derivatives in this case. So let's calculate the antiderivative. So we will use the same Newton-Leibniz formula. So x cube y plus 1 over 4 y in power of 4, and bounds of integration, yeah, let me not forget them. So from x over 2 to x. So now we will substitute these values. Now let we maybe expand this window. So what we have now? So with the substitution, so substituting x, first of all. So x in power of 4 plus 1 over 4 x in power of 4. And minus 1 over 2 x in power of 4, and plus 1 over not 32, 1 over 64 x in power of 4. So now we came to a definite integral that we already know how to calculate. So now let's simplify it first of all, and then we will calculate. So 1 over 64, so 33 over 64 plus 16 over 64. So it will be 49 over 64. And then, yeah, let's also add this value. So 64 plus 49, 113 should be, if I'm not if I calculating correctly. 113 over 64, and we have the following integral. So now we do the simple stuff. So it will be 1 over 5 x in power of 5, and with bounds integration from 0 to 4. So what do we actually have now? So 4 in power of 5. Now we can simplify it a little bit. So 64 is x is 4 cube. So 113 by 16 and divided by 5. So now uh, let's stop doing arithmetical stuff, and we will continue. We will concentrate on integration. Any questions about this exercise? Of course, when doing your individual tasks, you will have to uh, write. So you have to do to go by the to the end. Mhm. Stop. Why 32? Yeah, it was a mistake because so 16 by 4 equals 64. Yeah, so actually I need to recalculate it. And now we have the next integral. So 3b. So uh, y cube over x square. So the domain is the following. So parabola uh, y equals x square root of x, and straight lines. So y equals x over 3, and x equals 1. So we have the following region. Hmm. Actually, that's a good question. How is bounded? So either this region or this. Okay, but let we go with this region. Yeah, but also we need, yeah, I need to provide more information that either x is greater or equals than 1 or less than equals than 1. So let's uh, decide that x is less or equals than 1. So this region. So now let's describe this regional integration. So uh, x reaches values from 0 to 1. So it will be easier to integrate, so outer bounds of integration by x and inner by y. And y is bounded by functions x over 3 and square root of x. So now let's rewrite this integral with the assigned bounds or the assigned limits from 0 to 1 dx and y from x over 2 or x over 3 to square root of x. Uh, Now we can simplify this integral a little bit. So we have here we have kind of division, and we can move x to the outer integral. So 1 over x square. So in such case, if we have a product, so we can do the following stuff. So now is correct. And it will simplify our life. So now, what are we doing now? Well, yeah. Now let's calculate the antiderivative of y. So 1 over 4 y in power of 4. So we have the full integral, and now let's do the substitutions. So let's move 1 over 4 out of the integral. So what do we have? X squared minus x in power of 4 over 81. So 3 in power of 4 equals 81. So we have the following definite integral. We can also simplify it. So it will be equal 1 minus x squared over 81. Now let's integrate. So 1 over 4 and with the substitutions, so from 0 to 1, and what do we have here? X minus x cube over 243. So now substituting substituting 1. Actually, what we have. So yeah, we don't need these substitutions anymore. So what do we have? Damn it. So 1, oh no, not 1, 242 over 4 by 243. So now let's even simplify it a little bit. 141 over, yeah, so we'll multiply it by 2. 486, and I guess it oh yeah, it can be even divided by 3, by the way. So 141 over 3 equals 47 by 142. So now this is it's a final answer. Yeah, so we cannot cancel it anymore. So any questions about this exercise? Okay, I
No
guess
question.
no questions. Yeah, so we can even simplify it. So now we have to calculate the area of the region. So of course, integrals just integrals just for integrals are useless, but we will now practice in application of double integral. So we will calculate the area of the region. So first of all, let's solve for A, and let's plot their region. So y equals x, y equals 5x and x equals 1. So we have such a triangle. So this triangle. How to calculate the area using uh, a double integral? It is even so. As for me, it is simpler than using just definite integral. So we just need to integrate. We need to calculate such integral. So we need to integrate number one uh, in this region. And now let's assign uh, limits of integration. So x from 0 to 1, as we know from the conditions. And what about y? So the bottom limit is x, and the top limit is 5x. So now let's assign bounds of integration. So x from 0 to 1 and y from x to 5x. So now let's write everything in details. So we have y with the substitutions from x to 5x. So it will be equal to 4x. It makes no sense for me to write the difference in details. So, and now integrating this stuff. So it will be 2x squared with limits of integration from 0 to 1. And it will be equal to. And by the way, if we look at this plot, it will look like 2 square units. So if we put everything together. Any questions about this exercise? For A. Okay, if no questions, let's move to 4B. And now we will calculate the area of another region. So bounded by the following curves. Square root of x, 2 square roots of x, and x equals 4. So the following integral. So let's determine the bounds of integration, limits of integration. So for x from 0 to 4, as we see from a condition and from the plot. And what about y? So from square root of x to 2 square roots of x. And now let's integrate. So from 0 to 4 dx, and the inner integral. So from square root of x to 2 square roots of x dy. So again, so y with the following substitutions. So it will be square root, we will integrate just square root of x. And the antiderivative is the following. 2 over 3 x by square root of x, and from 0 to 4. So substitute in 4, and what will we receive? So 2 over 3 by 4 by 2. So it is 16 over 3. Any questions about this exercise?
No questions.
Okay, no questions. So now it is time to have a break, and then we will solve tasks with other usages of double integral, such as calculating volumes, static moments, mass, and so on. And now have a break for 5 minutes. Okay, let's continue. The next task is to calculate. So the task number A is calculate the volume of the body G bounded by two cylinders and planes. So let's try to plot in 3D. Square root of x, so y equals square root of x, and y equals 2 square roots of x. So plot these cylinders. Now x equals z equals 0, and z equals yeah, x plus z, so z equals 4 minus x, let it be so. 4 minus x. So we have such a region, so bounded by these cylinders and this planes. So actually we have a better graph here. So actually that's just for understanding how it looks like. The body that for which we need to calculate the region of integration. So now let's so then we will do the following stuff. We have to plot the projection graph of projection of this body on the plane x or y. So forward cylinders, and then how to find this bound. Actually we just have to so we need to find so from equality of these planes. So 0 equals 4 minus x. So and it means that x equals 4. So the following region will be the projection. And how to calculate the volume? So we will have the following formula. So volume by using a double integral. So it will, so d is the projection, and we have to calculate so the following stuff. So z by z dx dy. If we substitute, so we will receive we will receive z equals 4 minus x. So we will have to calculate this integral. Let's determine bounds of integration first of all. So x reaches values from 0 to 4. It will be the outer variable. And what about y? So from square root of x to 2 square roots of x. So now let's assign bounds of integration. So from 0 to 4 dx, and from square root of x to 2 square roots of x. So now integrating by y. So it will be equal the following. Yeah, of course. So using Newton-Leibniz formula. So for y minus xy with the following substitutions, dx. So now let's substitute these square roots and what we will receive. So in the first case, for square roots of y, minus 2x square root of x. Oh, yeah, square root of x here must be. And minus 4 square roots of x and minus x square root of x. So now let's simplify this expression. So what we will receive? So 4 square roots of x and minus x square root of x. Dx. So now we can integrate this expression. So what do we have here? So for the first addend, 8 over 3x square root of x minus 2 over 5 x x square root of x with the substitutions from 0 to 4. So it will be equal. So 4 here by 2 by 16 by 2. So now what do we have now? Okay, let's try to simplify a little bit if it helps us. So so 64, so 64 over 3 by minus 64 over 5. Okay. So let's move 64 out of brackets for now. So 1 over 3 minus 1 over 5. So 5 over 15 minus 3 over 15. So it will be equal 128 over 15. So it's done. Any questions about this exercise?
No question.
Okay, no questions. And let's check here. Yeah, 128 over 15. Now the following task. We need to calculate the mass and average density over plate D bounded by the following lines. Y equals x squared and y equals 1. And we have the density, which is given by the function x squared plus y squared. First of all, let's build this plate. So y equals x squared, y equals 1. So the following plate. And how can we calculate the mass? We will use the following formula. So double integral from the density. So actually like a usual double integral. So if we assign, so we, well, when calculating just a usual double integral, and if we think that it is the integrand is the density, we calculate some kind of mass. But yeah, actually the usual integral can be um, uh, negative, yeah, but mass shouldn't be negative, of course. And here the expression is a positive function. So x squared plus y squared. So now let's determine bounds of limits of integration. So for x, we'll integrate from -1 to 1. Yeah, of course, it is good idea to solve the equation x square equals 1, but yeah, when it can be easily solved. So x from -1 to 1. And what about y? Y reaches values from x square to 1. So now let's assign these values in the integral. So dx and x from x squared to 1 and this expression by dy. So now let's integrate firstly by y. So x square y plus 1 over 3 y cubed. Okay, now let's substitute these bounds of these limits of integration. So what we will receive? So substituting 1, we have the following expression, and when substituting x square, so x in power of 4, and here x in power of 6. Okay, let we also expand brackets. So minus 1 over 3x in power of 6 minus x in power of 4 plus this expression. Uh, Okay, we can even simplify a little bit these calculations. So as we can see, this function is even. So we have only even degrees. So we can use the following simplification. So we can integrate from, so we can calculate two integrals from 0 to 1. And now calculating the integral itself. So minus 1 over 21x in power of 7 minus 1 over 5x in power of 5 plus 1 over 3 x cube and plus 1 over 3x. We'll just erase x. Okay, let me calculate this integrals. Oh, okay, these fractions. Let's see. Let's look into my materials. I lost 2, by the way. That's bad tools. Multiplies. So yeah, actually here is everything right. So 88 over 105. Let's believe this recordings, because I don't want to calculate fractions now. Okay, so we found the mass, and also, if I'm not mistaken, we need calculate the average density of the plane. How to calculate average density? It can be found by the following formula. So we will divide mass by the area. So now we have to calculate the area of this region. So it is easier than calculate the previous integral. So let me copy and paste some stuff. So the following integral for calculating area. So here actually we will have 1 minus x square. And again, this function is even, so we can simplify a little bit. One minus 1 over 3, not 1, x minus 1 over 3x cube, and from 0 to 1. So 2 by 1 minus 1 over 3. So actually it will be 4 over 3. So now calculating the average mass. So 88 over 105 and multiplied by 3 over 4. So now what we will receive 22 by 22 over 35. So this is the average density. Any questions about this exercise?
No question.
Okay, no questions. And let's move to the next task. It will be the last task for today. So we will have to find static moments with respect to coordinate axes and the center of gravity of the following plate, bounded by a sine curve and values of x from 0 to p, and the x-axis. So actually, let we first of all calculate the first of all let's plot this region. So y equals sine of x, y equals 0, x equals 0, x equals p. So we have such a segment. So this plate. So let's describe let we first of all describe this plate, and then we will do other stuff. So x from 0 to p, and y from 0 to sine of x. So just so assigned limits of integration. And how to calculate static moments uh, with respect to different x's. So for x, the following the following integral. So x over x multiplied by okay, I don't remember if we have to multiply by the density or not. Let me remember it a little bit. Just a moment. If I guess we have to do it, but for this case, mu is a constant. So yeah, actually static moments are the following. So for x, multiply y by mu from xy. Yeah, and by the way, it must be a double integral. And for analogically for y, we swap variables. So yeah, and in our case, so from conditions so the density mu equals 1. That's why it's easier for us. So now let's calculate static moments first of all. So x is from 0 to p. Where and y is from 0 to sine of x. So now we will integrate actually a sine of x from 0 to p. And it will be minus cosine of x So cosine of p is -1 and cosine of 0 is 1. It will be equal to. So minus, and there -1, -1. And what about, oh, no. It was a mistake. Sorry. It was a mistake. So let's write the details. Let we not skip them. So so 1 over 2 y in power y square. So not yeah. So it is not so complicated integral, but yeah. Anyway, we need to calculate it. So 1 over 2 goes here, and sine square of x. So yeah, we will have to do a little bit more calculations. So 1 over 4, and here we will use formula of degree downgrade. So 1 minus cosine of 2x. So now calculating the antiderivative for this stuff. So it will be equal x minus 1 over 2 sine over 2x, and with substitutions from 0 to p. So sine will go away, and we have p over 4. So it's done for x. And what about y? So in this case, we multiply by x, and the bounds limits of integration are actually the same, but we have the following stuff. Let's move x to the outer integral. We can do it. And now we will substitute y. Yeah, so let we not skip details. So y with the substitutions from 0 to sine of x. So this integral will be calculated by parts. So u equals x, du equals dx, dv equals sine of x, and sine of x dx, and v equals cosine of x minus cosine of x. So minus x cosine of x with substitutions from 0 to p. Minus, yeah, actually plus, because we have minus here. So it will be integral of cosine of x. So let's calculate this stuff. So minus p by cosine of p. So it will be p. So P by -1 and by -1 here. So P, and if I substitute 0, it will be 0. So P and plus sine of x with the substitutions from 0 to P that actually equals 0. So the final answer is P here for static moments. So static moments are found. What else do we have to do? We also need to find the coordinates of mass center. So how to calculate them? Coordinates of mass center are found by the x with index c equals, so we divide static moments relative the y by s, and for y coordinate vice versa, so analogically. Now let's calculate the area of this region. So it will be calculated by the following integral. We just integrate 1. So what do we have here? So it will be sine of x dx. So we integrate sine, and we will receive minus cosine of x with substitutions from 0 to b, and it will be equal to. So now we'll calculate the coordinates of mass center. So P over, so yeah, for y, P over 8, and for x, P over 2. Yeah, and how to finally write the coordinates of the center. So the best idea to write them like this. So like points with the coordinates. Point with coordinates. Any questions about this exercise, about the whole lesson, previous lessons? Okay, I guess that no questions. By the way, I have checked all individual home tasks that you submitted up to this moment. Pay attention to comments that I left. If you have some questions, feel free to ask. And now have a nice day, stay safe, goodbye. Thank you for your attention.
Thank you for
Thank
watching.
you. Goodbye.
Goodbye.